Okay, let us talk about the principle of superposition. If you may recall, we use the principle of superposition in the mechanics of material. When we have the final examination in the problem 4, you may remember the problem asks us to determine the deflection at the middle of the beam, and the beam subjected to types of loading. One is 2 kN per meter, another one is 8 kN. By considering this and using the principle of superposition, in which the beam will behave in the linear elastic region under the application of the force, and also the deflection here gonna be very small. This is really true for our civil engineering structure. As you may know, we limit the deflection of the beam to span or the length of the beam divided by 240 if the beam has no wall below it. And we limit the deflection to the length divided by 330 if there is the wall there. So 300 centimeter beam, we will limit the deflection to be only 1 centimeter. So most of our beam in civil engineering will have very small deflection and will behave in the linear elastic manner. And then we will separate this beam into two beams. And then we use the deflection table to determine the equation of the deflection at the middle of this beam and also at the middle of this beam. Then by the principle of superposition, we will combine V sub C1 with V sub C2 to obtain the total V sub C. This is the example that we have. And then the principle of superposition not only apply to the determination or determining of the deflection, is also used in the determining of moment and the stresses. Consider the top beam. This beam subjected to 20 kilonewton moment on the left and 20 kilonewton moment on the right, and also the 5 kilonewton per meter uniformly distributed. And then we separate the beam into three beams by principle of superposition to be the beam with the 5 kilonewton per meter plus the beam with 20 kilonewton meter on the left and plus the beam with 20 kilonewton meter on the right. And then if we know the moment of the first beam, the moment of the second beam, and the moment of the third beam, then we combine them together to get the moment diagram of the top beam. And then the value of the moment on the left will be determined by 0, minus 20, and minus 0, so it's going to be minus 20. And 90 minus 10, we obtain 70 kilonewton meter at the middle. And on the right, we're going to get 0, and minus 20 is the value of the moment on the right hand side. By doing the same like this, we can use the result of the more simple beam and combine them together to get a more complicated beam. Okay, and then when we arrive at the maximum moment, we can determine the maximum normal stress equal to the maximum moment time distance y and divided by the moment of inertia I. The principle of superposition have the limitation for large deformation because for large deformation, the distance d is the moment arm due to the applied force will change with the size or magnitude of the beam. Like for this one, if the applied force, the total is 10 and this is 6 and this is 4, since the distance d1 and d2 are not equal, so the moment p times d will not equal to p1 times d1 plus p2 times d2, like this example. Okay, in conclusion, the principle of superposition apply for the structure with linear elastic behavior, and the deformation or the deflection of the structure supposed to be very small, and then it can use to find the total deflection. It also can use to find the resultant moment, and by the resultant moment you can find the resultant stress as you wish. Okay, and we will talking about this principle of superposition more detail when we study what related to this principle. Now we go next to the equation of equilibrium. But before we go to the equation of equilibrium, we got to know the Sir Isaac Newton. Sir Isaac Newton is the great scientist of the 17th century. His Newton's theory of motion is important, same as the relativity theory of the Einstein. He think about the three laws of motion for quite a long time until one day afternoon he sit down under the apple tree, and then the apple dropped from the tree to the ground, and he popped out the idea that there must be a drawing power in matter. And by this word of seeing the apple fall to the ground, he got the theory about gravitation. This is called gravitational theory. That means this equation used to find the gravity between two mass m1 and m2. By the gravitational theory, Sir Isaac Newton produced three laws of motion. The first one, summation of F of force equal to mass times acceleration. And this equation come to the equation to find the weight of a mass on the earth, in which W equal to mass times gravitational acceleration. And when the A is 0, that means when the structure is static or the structure moves with constant velocity, we got the second Newton law, summation of force equal to 0. We use a lot of second law to determine the reaction, to determine the internal forces and internal moment of the structure. And we use the forces and moment to design the structure, to design the machine. And then the last one of the law of motion is the third law of motion, the action equal to the reaction. So the main thing is the second law of motion. By the second law of motion, when we apply this second law of motion to a two-dimensional structure as shown in this picture, In the application of the 60 Newton and the moment 90 Newton meter, if this structure gonna be in equilibrium or in statics, the summation of the force in the x direction must be zero. That is, no movement in the x direction. And the summation of the force in the vertical direction is zero. That means no movement in the vertical direction. And if you like to prevent the rotation, the summation of all the forces, the action force and the reaction force, must be zero. So by these three equations of equilibriums, we can use it to determine the three reactions acting on the structures. Okay, and from this, since the A is the pin, there is two reactions, and the B is the smooth surface. It's going to have only force there. And to apply these three equations, the order of using is important. Usually, we use the summation of moment equal to zero, since when we took the moment, for example, at A, the force A sub x and the force A sub y gonna be have zero effects on this equation, and then we can determine the force acting at B. And then after that, you use the summation of f sub x equal to 0 and summation of f sub y equal to 0 to determine the other unknown reactions. I should note that since this structure has the unknown reaction equal to the number of equations of equilibrium, this structure is called statically determinate structure, and we will talking about that later. Okay, in the real life, some of the structure is in 3 dimensions. Now we have like 5 tower crane in my university, in our university. You may have a chance to take a look 2 of them if you go to in front of the library. The tower crane is a good example of 3-dimensional structure. The support at the A of the tower crane supposed to be fixed in order tower crane to be in equilibrium. If this structure will be in equilibrium, that means the force that acting on it, the force vector that's acting on it must be 0. The moment vectors that's acting on it also must be 0. Since the force can be separated into the force in the x direction, into the force in y direction, into the force in z direction. So we're going to have 3 equations of force to be in equilibrium. And also for the moment, there are 3 of them: summation of moment about x-axis, summation of moment about y-axis, and summation of moment about z-axis. That must be 0. So to make this guy, this tower crane, to be in equilibrium, the A sub x need to be balanced the force in the x direction, and the reaction A sub y for the y direction, and the reaction A sub c for the z direction. These 3 forces prevent the linear movement, and there are another 3 moments to prevent the rotational movement: the m sub x, the m sub y, and the m sub c. Okay, and luckily this course we will not talking about the 3-dimensional structure as we have in the static. So the main equation of equilibrium that we are going to use is only in 2 dimensions. Then if we cut the structure as a point, usually we have shear and the moment. If we cut it and then we consider the left segment, the downward shear gonna consider positive shear, and the counterclockwise moment gonna consider as the positive moment. Okay, and by using the third law of Newton, if you consider the right hand side segment, the opposite shear and opposite moment also are positive. Okay, let us go to the next thing. We are going to talk about the determinacy and stability of the structure. This section gonna be the problem in our midterm examination. The first part, we're talking about the one-way action and two-way action. And the second part of the problem, the first problem in the midterm examination, gonna talking about the determinacy and stability. The concept about the determinacy is simple. Structure, when it's subjected to the forces, is going to have the unknown reaction and unknown internal forces and moment. This unknown, when compared to the number of equations of equilibrium, if they are equal, the structure will call statically determinate structure. Like this one, this is the pin. The pin gonna have 2 reactions, and this is the roller. The roller gonna have 1 reaction. The total of the reactions here is 3, is equal to equation of equilibrium. And then if we change the support from the pin to the fixed support, from the roller to the fixed support, the number of the reaction forces and moment will change. The fixed support gonna have 3 unknown action and moment, and another 3 here. So the total number of unknown reaction include forces and moment gonna be 6. And we have only one member. One member have 3 equations of equilibrium. So the unknown is 6. The equation is 3. This structure called statically indeterminate structure with 6 minus 3 equal to 3 degree of indeterminacy. In conclusion, one structural member have 3 equations of equilibrium. So if we have n structural member, we're going to have 3n equation of equilibrium. That is the number of equations. And the R is represent the unknown reaction and unknown internal forces and moment. So if the unknown R equal to number of equations, the structure called statically determinate. If the unknown is larger than the number of equations of equilibrium, that structure called statically indeterminate structure. Okay, let's take a look at this example. We will demonstrating the structural member or structure as statically determinate or statically indeterminate. If statically indeterminate, what are their degree of indeterminacy? This is simple beam subjected to the external green force. And if we consider this is pin, the pin gonna have 2 unknown force. and this is roller is got another one unknown force. So the total R here is going to be 3. And since the beam is one free body diagram, so the number of equation that we have is going to be equal to the number of the unknown. This beam is statically determinate beam. Now we have close to the same beam, but we change how we support the beam. We change the roller support to be the fixed one, and then we put one more roller here. What's the number of unknown reaction? Pin 2, roller 1, and fixed is 3. So it's 3 plus 1 plus 2. The R is total is 6 unknown. And then we have only one free body diagram of the beam. So the equation is going to be 3 times 1 is 3. So the unknown is 6. The equation is 3. The structure is going to be 6 is unknown. And 3 is the equation. The structure is going to be statically indeterminate structure with 6 minus 3 equal to 3 degree of indeterminacy. This picture is a frame, and this frame has the fixed support here for the column, and then it has the pin support here. This problem is special. The column and the beam have the hinge connection here. The hinge, as we know in the static, when you draw the hinge gonna have 2 unknown forces there. So the unknown here gonna be 3 for the fixed support, 2 for the pin, and another 2 for the hinge. So it's gonna be 3 plus 2 plus 2. The total unknown is 7. And then the number of free body diagram of the structural member will be 1 for the column, another 1 for the beam. So the total equation of equilibrium is 3 times 2 is going to be 6. Okay, the unknown is 7. 3 plus 2 plus 2. And number equation is 3 times 2 is 6. 7 minus 6. 7 is less than 6. The structure is statically indeterminate frame with 1 degree of indeterminacy. Okay. Next, conform to another frame, have 3 members. The column have the rigid support with the beam. The beam have rigid support with the column. And then the support here is pin, 2 unknown, roller, 1 unknown. So the total unknown is going to be 3. And we have 1 free body diagram. The number of equation going to be 3 times 1. So the unknown equal to the number of equation of equilibrium. This frame is statically determinate frame. Next, come to the frame with 2 story. Okay, this is first story, this 2 story, that this is the roof. For this one, since there are the beams connects the column, 2 of them, we got to cut the beam. When we cut each part of the beam, we will have 3 unknown there. One is normal force, one is shear, another one is moment. So this is going to be 3 unknown, and this is going to be 3 unknown. This is going to be unknown forces and moment. And then that's it, internal unknown forces and moment. And then if we consider the support, each of them fixed could have 3. This is also have 3. So the unknown reaction is 6, 3 plus 3, and unknown internal force is going to be 3. It should be noted that over here we count only 3, not 6, because we use the third law of Newton. So the magnitude of the force and the moment are equal, but just opposite direction. So unknown here is 3, and this one is 3. So the total R is 3 plus 3 plus 3 is going to be what? 12. And the number of equation for one free body diagram is 3. Another one is 3. So it's 3 times 2 is 6. So this problem R is 12. Okay, and N is 2 times 3 equation of equilibrium is going to be 6. So unknown larger than the number of equation by 6. This structure is statically indeterminate frame with 6 degrees of indeterminacy. Anyway, we're supposed to know that in some more complex structure, such as the RC building with 2 stories or more, actually, if the support of the frame are fixed, we can cut the beam and count each cut going to be 3 unknown, and 3 unknown, we arrive the frame have 6 degrees of indeterminacy at what we generally use to determine on this table. Okay, next, let us consider the stability. Let me conclude before this. If the unknown forces and moment equal to the number of equation of equilibrium, the structure is statically determinate. If the unknown is larger than the number of equation of equilibrium, the structure is statically indeterminate. The degree of indeterminacy is the number of unknown minus the number of equation of equilibrium. For the stability, okay, sometimes when the structure have the unknown reaction equal to the number of equation of equilibrium, and the structure still not be in equilibrium. For example, this beam. This beam has the roller support at A, B, C, and you know that the roller support can provide only the vertical direction reaction. So the free body diagram of this one going to be like this. And if you summation of x sub x equal to 0, you will see it won't be 0. This beam going to move to the left. So when we consider the stability, if the structure is improperly constant for the parallel reaction, the structure is unstable. There is another thing. If the supports are arranged such a way that the reaction cut at one point, like this beam, we can see that if we draw the free body diagram of this beam, and then we take the moment at O, F sub A won't produce any moment, the same as F sub B and the same as F sub C. So the summation of moment going to be P times D, and then it won't be 0. So for the concurrent reaction, the structure is unstable. And the last one, insufficient constant structure. That means R is less than, the R is unknown, is less than the number of equation of equilibrium. For this frame, we have only 2 roller, so the reaction is only 2. And one free body diagram, we have 3 equation of equilibrium that are less than 3. So it is insufficient constant frame. Okay, let us go to the next example. We're going to check if the following structural member and structure are stable. If it is stable, they are statically determinate or statically indeterminate. If it is statically indeterminate, what are their degree of indeterminacy? Let's consider the frame AB. The A is pin, the B is roller. This frame gonna have 3 reactions, and then R is equal to 3. And then the number of equation of equilibrium 3 times 1 free body diagram. So R is equal to 3n. This is stable and statically determinate frame. The second example, A is fixed, C is hinged, and B is fixed. So the total unknown going to be 3 plus 3 is 6. And since we have hinge here, the total unknown is going to be 8. And the beam will be separated into 2 pieces, AC and CB. So the number of equation of equilibrium going to be 3 times 2 is 6. Structure is statically indeterminate because unknown is 8. And number of equation of equilibrium is 6. And it is stable. And the degree of indeterminacy is going to be S minus 6 is going to be 2 degree of indeterminacy. Okay, coming into this beam. This beam has the roller support at A, at B, and C. You can see that the reaction is going to be only in vertical direction. Even though the unknown reaction is 3 is equal to the number of equation of equilibrium, but due to the horizontal force, this beam gonna move to the right, so it is unstable due to parallel forces or parallel reactions. Okay, coming into this frame, have the pin at A and the pin at B and the roller at A. The roller at A is specially rearranged until the line of action of the reaction at A cut at B. By doing this, we got what? All the forces are concurrent at B. So if we take the moment at B, the green force will multiply the eccentricity or moment arm here, and the summation of moment at B is not 0. So this is unstable due to improper constraint with concurrence reaction. Again, this is also interesting structure. There is 3 parts of them. One is AB, another one is BC, another one is CD. The B is the hinge and the C is the hinge. When the support at A is pin, the support at B is hinge. The support at A is roller, the support at D is pin. So the total reaction going to be 1 plus 2. And due to the hinge here, the reaction and no reaction is 2 and 2. So it's only 1 plus 2, 3, plus 2 is 5, plus 2 is 7. The total unknown is going to be 7. The number of equation of equilibrium going to be 3 times 3 pieces is going to be 9. So this problem, we have the total reaction of 7. And then the number of equation of equilibrium is 9. So this structure is unstable due to insufficient constraint. Okay, the part of checking the stability and checking the determinacy of structure, we need to compare the unknown reaction with the number of equation of equilibrium. If they are equal, the structure is statically determinate. If the unknown is larger than the number of equations of equilibrium, the structure is statically indeterminate. And if the unknown is less than the number of equations of equilibrium, the structure is unstable. Anyway, the unstable structure also have another types to be considered. One is the parallel force. Another one is the concurrent force. By these two types, even though the unknown reaction equal to the number of equations of equilibrium, the structure also unstable. Okay, next, and we will talk about the application of the equation of equilibrium